Okay, this is a review of laboratories 3, 4, and 5. We'll start with laboratory 3. Use of the colorimeter and homeostasis. The colorimeter is, or spectrophotometer, is an instrument that is used to determine the concentration of a substance in a solution. They use it in agriculture. Most commonly it's used in a chemistry or in a clinical lab, like a hospital lab, where we do hundreds of different tests by the use of the colorimeter. The colorimeter is a spectrophotometer. It takes a light source. In order to work, it cannot use white light. It needs to break the light down into an individual wavelength. That's either done by one of three methods. You use a filter, you use a prism, or use a diffraction grating. The ones that we have in the lab use a diffraction grating. You want to have the color as close to that of the substance that you're measuring, i.e., if the substance is blue, you want the range of light down in the blue range. It can be used to measure the concentrations of various substances in the lab: glucose, lipids, protein, albumin, various other, calcium, phosphorus, proteins. It's all sorts of different concentrations in plasma, urine, or body fluids. Now, sometimes we will use a colorimeter to measure a substance that does not have color, and obviously it has to have color for a colorimeter to work. At that point, we will use an indicator. The one I gave you in class is, for glucose, we used to use what they call an O-toluidine. And you would put the sample in, and you would boil it, and it would turn this nice color of blue. And depending on how blue it is, you could tell how much glucose is in there. Now, a colorimeter does not work unless you have something to compare it with. In other words, if you want to know how much glucose is in a solution, you put it in a colorimeter. Unless you have a known standard to compare it to, you don't know what's in there. So you have to make a standard curve, meaning you would make a serial dilution of a known concentration of glucose, hopefully encompassing the range of the unknown, meaning if the unknown's at, say, 100 milligrams, you have a standard curve that goes from 50 to 400, so that you know the unknown is going to be somewhere within that range. And then you're going to make a linear regression, a curve, on graph paper, and then you compare the absorbance to the absorbance of the known standard. For instance, if the known standard had an absorbance or a transmittance of 0.5 or a transmittance of 50, meaning 50% of the light has gotten through, and your standard at 100, if the standard at 100 had a transmittance of 50 and you put your unknown in there and it came out with a transmittance of 51, you're going to know pretty close that your unknown has a glucose concentration of 100. By making a curve using serial dilutions, you can go up and down from there. Now, the other thing, a colorimeter, in order to work properly, it must obey Beer's law. Now, this is kind of a circular argument, but whatever measuring must obey Beer's law, as does a colorimeter. So Beer's law states that the concentration of a substance is proportional to the log of inversely proportional to the log of the light transmitted. Meaning, the more concentrated the substance is, the less light is transmitted through the spectrophotometer. Your parts: you have a light source, you have the filter or diffraction grating, you have the cuvette that holds the sample, and then you have a light meter or galvanometer. The light comes through, it goes through the cuvette, and the concentration of whatever's in the cuvette absorbs light. Less light is transmitted to the galvanometer. That's what's read, and that's how you tell how much of your subject is in there. Now, like we said, the the things that we measure with a spectrophotometer on a direct measurement must obey Beer's law. And Beer's law states that the concentration of a substance is inversely proportional to the logarithm of the amount of transmitted light, logarithm of the amount of light transmitted by the substance. So that's Beer's law. That's colorimeter. You're going, in a nutshell, you're going to shine light through it of a certain wavelength, close to that of the solute, and of the substance you're measuring, and you're going to compare that to a graph made of known standards, and through that be able to tell how much of that is in the specimen. Okay. Now we're going to go on to membrane transport and homeostasis. Homeostasis is defined as the maintenance of a relatively stable conditions or equilibrium, or much shorter, a dynamic constancy. Homeostasis, again, is a relative value. It is not a set or a static value. Your pulse rate, which we used in the lab, is relative. It's relative to your exercise. It's relative to a mean. That's why we took our pulse rate 10 times. We determined the mean, and then we graphed the rate on either side. And then they didn't all stay at the mean. They moved on various sides. That indicates a homeostatic mechanism, meaning that it varies around a mean. If it varies too much, then we start looking for a disease state. For instance, a normal range for glucose in a human would be 70 or 75 to about 110. The average would be 90, but if we measured everybody in the class, they would vary from anywhere from 60 to 120, up and down around the average of 90. That's okay. It's still a homeostatic mechanism. Now the body tries to maintain a range of values depending on what you're looking at, and let's use body temperature for one. And this again is a homeostatic mechanism. It's not a set. Your body temperature is not set. It varies. And the body maintains a range. Say if you are out in the sun and you're starting to overheat, your body starts to sweat. And the sweat on the surface of the skin cools it off and brings your body temperature back into range. So, an increased body temperature causes the body to sweat. The sweat is a negative feedback. With the negative feedback, it brings the temperature back down into the range where it's supposed to be. If you're out in the cold and you're getting moving toward hypothermia, your body starts to shiver. By shivering, you use energy, and it brings your body temperature back up into the normal range. Again, that is a negative feedback system. A negative feedback system when it is engaged, it negates the reason that it was engaged for. If your body is too warm, the sweating is engaged, and that negates the body being too warm. That's a negative feedback. If your glucose is too high, your body secretes insulin. The insulin brings the glucose down. So with the feedback from something that is abnormal causing the results to come back into the normal range, that is a negative feedback. Positive feedback is if something is going abnormal, then the reaction is to push it further into the abnormal. There are two systems in the body that do this, though ultimately they end up with a negative feedback, or else it would be simply a runaway reaction. Those are the secretion of oxytocin during labor, and the blood clotting system, or the coagulation cascade. Going on, like I said, a positive feedback causes a reaction to increase, and oxytocin, blood clotting. Negative feedback and homeostasis is involved in temperature, pH, osmotic regulation. breathing rate, pulse, cardiac rate, thyroid, and glucose, and many more. In the thyroid, you have the T4, that is the metabolically active thyroid, but you also have the thyroid stimulating hormone. If the thyroid, is too low, thyroid stimulating hormone is going to cause the increased production of thyroid. If the thyroid's too high, then the amount of thyroid stimulating hormone goes down and the amount of total thyroid goes down. Now, some of the systems are a little more delicate. For one would be the glucose. As an example, in the home, if you have a thermostat to regulate the heat of the house, you have the air conditioner running, and you have the heater running. If the house is cold, the heater is going to come on higher and push the temperature of the house up. If the house is too warm, the air conditioner is going to come on and push the temperature down. But by working with a system that forces the abnormal result in the opposite direction by two methods, one with the house, with the air conditioner coming on and the heat shutting off, or the air conditioner shutting off and heat coming on, you gain a much finer degree of regulation. So homeostasis is maintaining a normal constancy. It varies around a mean. The variance around the mean is what we call a normal range. We would have a range of values in humans that is considered normal. And for glucose, it's 70 to 110 for a human. We would take many, many samples. We would determine the average, or the mean, and then we would go 2 standard deviations on either side. That encompasses 95% of the population. So in all reality, just statistically, 1 person out of 20 is going to be marked abnormal when they are actually normal. But that's how the normal range goes. Let's go on here. We're going to talk about membrane transport. Actually, we're going to pause here because I think we're just about done. Excuse me 1 second. How long have we been going here? 13 minutes. Okay, we're going to stop.